Thanks, Alfredo, for the introduction, and thanks, and also for the invitation. So I was asked to talk about the primordial magnetic fields. So I'm basically going to talk about magnetic fields in our universe, which is something that I enjoy thinking about every now and then. And the reason for this is because I think that cosmological magnetic fields are a very good probe of physics beyond the standard model. And hopefully I will convince you on this point in the next 30 minutes or so. So parts of my talk will be based on these papers, which were works in collaboration with Andrei Beneviges, Atish Tabolkar, and the second one with Martin Slot. Okay, so here's the outline of my talk. So I'll start by giving a very quick overview of the observational suggestions or hints for the existence of magnetic fields in our universe. And then I'll move on to discuss how these magnetic fields may or may not be produced from standard model physics and beyond. And I'm not sure how this Zoom seminar is supposed to work, but if you have any questions during my talk, feel free to ask me at any point. Okay, so so observations. So observations, cosmological and astrophysical observations have revealed that our universe is magnetized on various length scales. So let's start from inside our galaxy, from our Milky Way galaxy. So what I'm showing you here is a map of the magnetic fields of inside our Milky Way. It was constructed by the Planck team through their analysis of the polarized emission from the cosmic dust grains, which are aligned by the galactic magnetic fields. So it's a pretty nice figure, and you can already see from this figure that there's abundant magnetic fields inside our Milky Way galaxy, and these typically have an amplitude of something like microgauss. Okay, so these are galactic magnetic fields. So now let's move outside of our galaxy into the intergalactic or extragalactic space. So interestingly enough, even in these intergalactic space, astrophysical observations from the past decade or two have been suggesting that there seems to be magnetic fields even in these regions. And these suggestions come from the observations of blazars, which are astrophysical objects that emit very energetic photons towards us. So the story goes as follows. So people have detected distant blazars that emit TeV photons towards us. So they basically detected these primary TeV photons from the source. So the next thing people tried to do was to look for the secondary cascade photons that should accompany these primary photons. And that's because when there's a TeV photon traveling in the universe, it should eventually interact with the extragalactic background light, which is basically starlight, and decompose into electron-positron pairs, which eventually would upscatter the CMB photons through the inverse Compton scattering up to an energy scale of something like GeV. So the point is that if there's a TeV source in the sky, it should be accompanied by secondary cascade photons with a slightly less energy. So people digged into the data searching for these cascade photons. But interestingly enough, people didn't find any of these secondary photons. So the question is, where did these photons disappear? Well, the interpretation of one possible interpretation of this is that this missing photons is induced by intergalactic magnetic fields, because if you have intergalactic magnetic fields along the way, the magnetic fields would bend the trajectories of the electrons and positrons so that even if they eventually upscatter the CMB photons, these cascade photons will be emitted towards some random direction, and therefore it can explain why we do not find these cascade photons associated with the source. And so many groups have done analyses on what kind of magnetic fields you actually need in order to sufficiently bend the trajectories of the electrons and positrons. And the result is that you need something like at least femtogauss magnetic fields in the intergalactic space, coherent over a rather large distance of something like megaparsec. So these are the observational hints for the extragalactic magnetic fields. So we have seen that both observational evidence or hints for both galactic and extragalactic magnetic fields. So the next question is, then where did these magnetic fields come from? So for these galactic magnetic fields with the size of microgauss or something, they have to start from something. I mean, they have to be seeded at some point. And studies typically say that these galactic magnetic fields have to start from something like a seed field of something like 10 to the minus 20 Gauss.
Sorry, can I make a comment at this point?
Sure.
So what you described was a non-observation of GeV emission from TeV source used as a hint for a magnetic field. In principle, to really claim detection, we would like, of course, to see this halo. So the GeV halo. So instead of disappearing GeV emission, we would like to see that it's a bit diffuse, and it's not possible with Fermi, but maybe possible with CTA very soon. So if we do observe, if we are lucky and observe these small halos, then we will be really sure that these magnetic fields exist. Just a comment, and also a question to use the opportunity. So where does this number 10 to the minus 20 comes from? I'm very curious.
So for these, they basically consider dynamo. And so if you have dynamo, and if you're going to produce something like a microgauss today, what kind of initial field do you have to start from? So they kind of do this inverse trick, and they get this number. Although the actual number can be quite different depending on the study. But the point that I just want to make here is that you have to start, even if it's tiny, you have to start from some seed field for the galactic magnetic field.
Mm-hmm. But then the uncertainty in this order is quite large, right? It can be.
Yeah, exactly. Did I answer a question?
Yes, thank you very much.
Okay, great. So thanks for the comment. And yes, so those are the, yes, I was saying that at the moment, there's no established theory for explaining the origin of these seed fields for the galactic magnetic fields. But the situation is even more complicated for these extragalactic magnetic fields because, so first of all, there's an upper bound on intergalactic magnetic fields from CMB observations, which is something like nanogauss. But now with these blazar experiments, now there's also a lower bound. So, so these are suggesting that the magnetic fields, intergalactic magnetic fields, should lie somewhere here. But the difficulty here with trying to explain these with astrophysics is that these are magnetic fields in the intergalactic void regions. So there's basically no matter, which makes it very difficult for astrophysics to produce these magnetic fields. And on top of that, these are magnetic fields with a very large correlation length, like at least megaparsec or something, which makes it even more difficult, if not impossible, for astrophysics to explain their origin. So the situation seems to be calling for a cosmological explanation for the origin of these magnetic fields. So now I'm going to switch gears and go to the theoretical side of the problem and discuss whether it is possible at all to produce these cosmological magnetic fields. And I will start from discussing standard model possibilities. Okay, so our question is, can magnetic fields be produced cosmologically? Well, here, magnetic fields is basically a collection of a large number of photons. And what does cosmologically mean? Well, cosmology basically provides us with a non-trivial gravitational background. So this question of can magnetic fields be cosmologically produced, this can be translated into the question of can photons be gravitationally produced? Well, generally speaking, we know many examples where light or massless bosons are produced gravitationally in the early universe. Probably the most famous example is the inflaton field, which is a nearly massless spin-zero boson. So what happens for the inflaton is that during inflation, the curvature of the de Sitter space excites the inflaton field, and the produced inflaton quanta basically sees the large-scale structure of our universe today. So this is basically the core idea of inflationary cosmology. And something similar happens also for the graviton, which is a massless spin-2 boson. And when the graviton is produced during inflation, it leads to primordial gravitational waves, which is what many experiments are actively searching for today. So, and since photons are basically a massless spin-1 boson, it's a kind of a natural question to ask. Do photons get produced gravitationally? But for the photons, there's one twist in the story because of the Weil symmetry. So here is the Yang-Mills action for electromagnetism, for describing classical electromagnetism. And this Yang-Mills action has a symmetry called the Weil symmetry, which basically means that when you multiply the metric by some overall factor, the action stays unchanged. So what this basically means is that as long as you are in a Weil flat spacetime, namely spacetimes like the FRW metric, which can be connected to a flat Minkowski space through an overall factor, the equation of motion of the photons takes exactly the same form as in flat Minkowski space. So in other words, the Maxwell equation takes exactly the same form whether you put your photon in a flat Minkowski space or whether you put your photon in a expanding FRW universe. So in this sense, photons do not really feel gravity in an FRW universe. And if they do not feel gravity, of course, they cannot be produced gravitationally. However, the story is different at the quantum mechanical level because these kind of scaling symmetries are actually broken at the quantum mechanical level due to charged particles running in the loops. So in other words, the Weil symmetry is anomalous. And when you look at the quantum effective action, that does change its form under a Weil transformation. So in this sense, at the quantum mechanical level, photons do feel gravity. And if they do feel gravity, you start to have this hope that maybe at the end, they do get produced and form primordial magnetic fields. And this is something that has been studied for quite a long time, since when Dolgov pointed out this possibility in 1993, because the point here is that this Weil anomaly, this is intrinsic to QED, so it's basically intrinsic to the Standard Model. So if the Weil anomaly can induce any sort of magnetic field production in the early universe, this will be like the most easy, or it will be the easiest, or the most natural way of explaining the origin of the cosmological magnetic fields. And so there has been quite a lot of works on this topic, but with very little consensus. And so let me explain the reason for the confusion. So in order to capture the physics of the Weil anomaly, what you want to do is that you want to compute the quantum effective action for the photon, which you can do basically by computing the loop corrections through the photon propagator. And by the way, here I'm talking about the very early universe, so times before the electroweak phase transitions. There's massless charged particles running in the loop, and I'm actually talking about the UN hypercharge field. But anyway, the point is that you can compute the quantum effective action for the photon, for the UN gauge field. Since we're interested in the early universe, so we're interested in a cosmological background, so you want to do this in a curved space. And this is also possible by considering deviations around the flat Minkowski space and inserting the interaction with the curvature of the space-time order by order. And Barvinsky and Vilkovitsky constructed a formalism for doing this in full generality, which is very nice. But the difficulty with these kind of studies in cosmology is that these kind of perturbative expansion breaks down in a cosmological setting. And the reason is because the cosmological spacetime is not just a small perturbation away from the flat Minkowski space. So this is basically, because the second derivative of this h is basically the Ricci scalar, expanding in terms of this h is basically, it's not a derivative expansion, but it's a curvature expansion. The point is that the curvature of the space-time can be quite large, especially if you go back to the early universe. And so, so basically, you cannot obtain the effective action in the early universe by doing these kind of perturbative expansion. And this was one of the reasons why all these previous works on the Weil anomaly magnetic field generation didn't agree with each other. People simply didn't know how to compute the quantum effective action. So, so this has been one of the problems, but there has been one breakthrough for this problem. And these people noticed that actually you can add up the curvature expansion up to infinite orders if your theory is classically Weil invariant, and also if your space-time is Weil flat, namely if your space-time is connected to the flat Minkowskis through a Weil transformation. So the basic idea is as follows. So by definition, the Weil anomaly is the functional derivative of the quantum effective action in terms of the Weil factor, which I'm writing as omega. So having said that, you can obtain the quantum effective action by integrating over the Weil anomaly. And by the way, here I'm obviously being very schematic because this is actually a functional integral. It's more complicated, but this is basically for delivering the basic idea. So you can compute the quantum effective action by integrating over the Weil anomaly. However, normally this doesn't really tell you anything because there's always integration constant part or a Weil invariant part, which can contain all sorts of non-local operators, and you have no idea how to fix. And this is generically the problem about computing quantum effective actions. But the main idea here is that if you're focusing on Weil flat spacetimes, then you can uniquely fix this part by requiring that your quantum effective action reduces to the familiar quantum effective action computed in flat Minkowski space when you go back to Minkowski space. So by using this trick, you can uniquely fix this part and obtain the quantum effective action. For the photon in an FRW universe, at the one loop level, this is the quantum effective action, corresponding to adding up the curvature expansion up to infinite orders, which looks quite simple. So this beta is the beta function for the gauge coupling. A is a scale factor, and M is a renormalization scale. And the interpretation of this is very simple. It basically just corresponds to the logarithmic running of the gauge coupling, not in terms of the co-moving momentum, but in terms of the physical momentum, which is the co-moving momentum divided by the scale factor. And because of this, now there's an explicit scale factor dependence in the quantum effective action, which basically shows that the photons actually do feel gravity at the quantum mechanical level. So now that you have the quantum effective action, you can go on and compute whether this leads to any sort of magnetic field generation. But then what we found was that even though the photons do feel gravity at the quantum mechanical level, the way they feel gravity is just too weak, such that the quantum fluctuations of the photons never get converted into classical and coherent magnetic field in the sky. So the point is that because this is basically associated to the logarithmic running of the gauge coupling, the dependence on the scale factor is only a logarithmic. And when you only have a logarithmic dependence on the scale factor, and when you compute the number of photons created, it's something like at most one photon in the entire observable universe. So I don't know how many photons you actually have to produce in order to create a coherent magnetic field in the universe, but one thing I can say for sure is that if you only have like one photon in the entire universe, it's obviously not enough to support a coherent magnetic field in the sky. So the result is that in contrary to a lot of these works on Weil anomaly magnetic field generation, actually there's no magnetic field production from the QED Weil anomaly. The Weil anomaly does not give rise to any production of primordial magnetic fields. And so what this is basically telling us is that because the Weil anomaly is pretty much the only way to violate the Weil symmetry within the standard model, this is basically telling us that standard model physics plus cosmology cannot give rise to a primordial magnetic fields in the universe. So the nice thing about this is that now we have an answer to the effect of the Weil anomaly in primordial magnetic fields, but we are still left with the question of then what magnetized our universe? So one way to go is to consider, instead of cosmology, consider more complicated small-scale astrophysics. And that may actually be the way to go for explaining galactic magnetic fields. And there are actually a couple of astrophysical theories that attempt to explain the origin of the galactic magnetic field. However, the situation is puzzling for the extragalactic magnetic fields because, as I said at the beginning, these extragalactic magnetic fields, as suggested by the Blazer observations, is that these are magnetic fields in the void regions where there's no stuff. And it's also magnetic fields that are coherent over cosmological distances. So it's very difficult for astrophysics to explain their origin. So this motivates us to go beyond the standard model. Okay. So the point with the beyond the standard model physics is that once you invoke beyond the standard model degrees of freedom, you can start explicitly violating the Weil invariance at the classical level, and then you can efficiently produce gauge fields in the early universe. And so, for example, you can introduce some sort of coupling between the gauge field kinetic term with some function of some new degree of freedom, for example, the inflaton. Or you can also introduce axionic couplings with an axion-like field, et cetera, et cetera. And by the way, I think you see these kind of theories quite often these days, also in the context of like axion physics or also vector dark matter or attempts to produce excite gauge fields in order to excite gravitational waves in the early universe. And so actually the physics of BSM primordial magnetogenesis has a lot to share with those kind of studies as well. But anyway, so the point is that with beyond the standard model physics, in principle, it is possible to produce magnetic fields in the early universe. However, studies over the years have revealed that even with BSM physics, it's quite difficult to produce the femtogas magnetic fields as suggested by the Blazer observations in a theoretically consistent manner. And the reason is because, well, once you start efficiently producing electromagnetic fields, you have to start worrying about their back reaction because you obviously don't want them to spoil the success of cosmology. You also have to be careful about not being in the strong coupling regime because once you start, when you're efficiently producing the gauge fields, quite often you realize that you're entering the strong coupling regime where you actually don't have any good theoretical control. And there's also the problem with the Schwinger effect. And let me briefly explain this because this actually gives the strongest constraint on BSM magnetogenesis. So just to remind you, the Schwinger effect is this effect such that when you impose strong electric fields on the vacuum, it gives rise to a pair creation of charged particles out of the vacuum. And why this is bad for magnetogenesis is because when you're producing magnetic fields, you also produce electric fields just from electromagnetic induction. And as the electric field becomes stronger, eventually it starts producing charged particles out of the vacuum because of the Schwinger effect. So it basically turns the universe into a good conductor. But of course, in a good conductor, electric fields short out and magnetic flux freezes in. So the Schwinger effect basically terminates the growth of the magnetic field production. So it basically shuts off magnetogenesis. And so, for example, if you take into account this effect for inflationary magnetogenesis models, where they try to modify the gauge field kinetic term by coupling it to some function of some new degree of freedom, then it turns out the Schwinger effect puts an upper limit on the magnetic field produced from these models of something like 10⁻³ Gauss on megaparsec scales. which is something of 15 orders magnitude smaller than what is suggested by the laser observations. So it seems that we're in some sort of trouble. I mean, if we cannot produce magnetic fields, even if we invoke BSM physics, it seems we are in a dead end. And the reason why, when you think about why it's so difficult to create magnetic fields in the early universe, all these problems like the back reaction, strong coupling, and the Schwinger effect, it boils down to one thing, which is that the magnetic fields, after they are produced, it redshifts like 8⁻⁴, because it's basically radiation. And because of this rather quick redshifting behavior, the magnetic fields quickly decay away. So in other words, in order to produce an observably large magnetic field in the present universe, you have to create a humongous amount of magnetic field in the earliest moments of our universe, which leads to all sorts of these issues. So this has been the situation, but recently with Martin Sloth, we noticed that this is not quite right. And the reason why we don't think that this magnetic scaling is correct is because it's not the magnetic field alone that redshifts like 8⁻⁴, but it's the sum of the electric and magnetic field that redshifts like 8⁻⁴, because the sum is what makes up the radiation density. And another important point is that the electric and magnetic fields, they can exchange power because Faraday's law allow for that. And so, for example, if you have an electric field larger than the magnetic field, then the electric field can source the magnetic field even after the magnetogenesis phase is over. And so it can slow down the redshifting behavior of the magnetic field. And actually, when you have a stronger electric field, the correct redshifting behavior of the magnetic field is something like this, which is slower than the traditionally assumed 8⁻⁴ in a decelerating universe. So the upshot here is that the actual magnetic scaling, the redshifting behavior of the magnetic field, can be much slower than what have been previously assumed. So in other words, by using the incorrect magnetic field scaling, you can end up underestimating the final magnetic field amplitude. And we found that in extreme cases, you can, by using the wrong redshifting behavior, you can underestimate the final magnetic field amplitude by something like 37 orders of magnitude. So it's quite a non-negligible effect. And we also noticed that some models that have been considered to be dead can actually create quite large magnetic field. And we also constructed some toy models that can actually produce the femtogauss magnetic fields in a consistent manner. And so at the moment, we're trying to build more explicit models, but that's under progress. Okay, so I think it's time for me to wrap up. So my message number one is that the QED wild anomaly cannot give rise to primordial magnetic fields. And so by saying this, this basically means that standard model physics does not give rise to any primordial magnetic fields. But on the other hand, beyond the standard model physics can, and especially when you take into account the correct magnetic field evolution after they are created, they can actually create a quite large magnetic fields at the level that is observable today. And so because magnetic fields can only be produced from BSM physics, but not from the standard model physics, primordial magnetic fields is actually a very good probe of beyond standard model physics. And so in this point of view, I find primordial magnetic fields quite exciting. And I think it's also a rather cheap way of looking for beyond standard model physics. But obviously, there's a lot of work to be done. On the observational side, it's very important to study more about what's actually happening with those laser observations. It's also important to think about more other independent observational probes of intergalactic magnetic fields. And on the theoretical side also, there's a lot to do. And so there's a lot of exciting avenues to study with these primordial magnetic fields. And so if you find it interesting, please join the game. So that's quite it. Thank you very much.
Okay, thank you. So questions from the audience?
Yes, so I have made a question the chat. In Sans Corona, there are observed localized flux tubes. There are bright lines seen by satellites. So maybe there is suggested that they have some topological mechanism which stabilizes these lines. So if there is such mechanism also in this largest case of galactic field, they could prevent a Schwinger effect, for example. I think at least weaken it. Maybe it is worth to consider.
Sorry, I didn't quite get it. Can you?
There is observed in Sans Corona that the magnetic field lines are not just are localized, create nearly one-dimensional structure. There is also hypothesized that they are stabilized by topology, like fluxons in conductors. If there is some such stabilization mechanism, it could weaken the Schwinger effect.
You mean stabilized within like galaxies or in the intergalactics?
That the lines are localized into nearly one-dimensional structures. Strong magnetic fields are localized. We see it in some.
Okay. So, so you're saying that you can also study the Schwinger effect in those places, or is that what you're saying? Or
you can write in the chat.
I'm only saying that if there is some additional stabilization mechanism for magnetic field, then the Schwinger effect couldn't destroy them. That's a suggestion.
if there's also electric fields left, but I mean, normally, so in the early universe, like before the universe turns into, I mean, you know, before the universe is reheated, I mean, when you create the primordial magnetic fields, you also end up producing electric fields. But eventually, when the universe gets reheated at some point, then the universe obtains charges. So the electric field, the primordial electric fields are supposed to disappear. I mean, that's, yeah. So the electric field, I mean, the primordial magnetic fields will stay, but the primordial electric fields will disappear at that point. So if you're talking about the Schwinger effect induced by the primordial electric fields, I mean, that can be a very important before the reheating epoch, but in the modern times, I don't think that would be the case.
Yeah.
Okay. There is another question from the audience, so please just unmute yourself and ask the question.
Hi, Takeshi. Hi, this is Rajiv Jain from Bangalore, India.
Hi.
Hi, how are you?
I'm well, yeah, great to hear from you.
Yeah, so I just wanted to get some clarification from you about this, the B field from Weil anomaly. Remember, there's this original Dolgoff's paper, and he also had this logarithmic correction arising from the loops, okay? And it's a very short, I think, physics letters B paper. He also concluded that there's actually no B field from the Weil anomaly, okay? Quantum corrections to Weil anomaly. So I just want to understand from you, what is different that you found in your paper compared to the original Dolgoff's paper?
Yeah, okay, yes. So thanks for asking. So in the Dolgoff's paper, he arrives at this action through sophisticated guesses, and so he arrives at this logarithmic effective action. But he also claims, so his claim is that if the number of charged particles is small, then the background dependence is only logarithmic, and it doesn't give rise to magnetic fields. But he claims that if there are abundant charged particles in the early universe, maybe from Young's matter model physics, then his claim is that the background dependence actually turns into a power law instead of a logarithmic. And then you can create huge magnetic fields. So that's his claim. However, what we basically showed is that independently of the number of charged particles, it's always the logarithmic dependence because it's basically associated to the RG flow. And as long as it's a logarithmic dependence, no matter how many charged particles you have, you can never create coherent magnetic fields.
Obviously, with the logarithmic growth, I mean, it's a very slow growth, and there's no way you can produce strong enough magnetic fields. Yeah.
Exactly.
Okay. Okay. Thanks a lot.
No problem.
Other questions?
Yes, I have a question about your no-go theorem about no B from standard model physics. So would you consider chiral magnetic effect as standard model physics?
Okay. I mean, okay, okay. But I guess here you have in mind something like chiral transport, or?
Here I have in mind that if somehow there is a disbalance between left-handed and right-handed fermions, for example, electrons, this balance can be transferred by purely standard model or electrodynamics physics into magnetic fields. And of course, creating this disbalance as an initial condition would require beyond standard model physics, but we know that we need it for baryogenesis, for example. So if for example, as a byproduct of baryogenesis or something else, we only created initial conditions where the densities of left-handed and right-handed electrons are not equal, after that, purely with electrodynamics, we can generate magnetic field.
Yeah, no. Well, okay, whether I call it standard model or beyond the standard model, I guess that's a matter of definition. But yes, I mean, that's a good point. I guess here you have to, if you want to produce like large-scale magnetic fields like those in the intergalactic space, you have to create, large scale of these stuff. Maybe you can do with using inflation. So that is a possibility. Probably you need some beyond the standard model physics to do that, but that could be a possibility. But here, yeah, you just reminded me, but I should also comment that you can also have a BM battery kind of effect with cosmological perturbations, right? And so at the second order level, the cosmological perturbations also induced BM battery effects, and that can actually produce large-scale magnetic fields. But I didn't mention about that because that's the effect is quite tiny because it's at the level of the second-order perturbation. So that is also another example where, that again, I don't know whether I should call it beyond the standard model or standard model, but that's also another way that, in principle, you can produce primordial magnetic fields, although the effect is tiny.
Yeah. Thank you. Also, I have a very small philosophical comment about your statement that it is cheap. I mean, of course, we are all poor theorists, but for the real physicists who do experiments, right, it's not cheap because even with CTA, is not clear whether they will be able to detect really magnetic fields. I mean, this depends on how far in the high energies the spectra of blazars continue and so on the CTA actual performance. So it's very, very expensive actually, although I agree that it's extremely exciting because this is not only beyond standard model physics, but potentially also another probe for the early universe that will be an older relics and BBN, which of course is a big thing. I absolutely agree, but by no means, unfortunately, it is cheap.
Yes, I mean, yes, thanks for the comment. Yeah, I mean, I was comparing with like the next generation colliders, but I agree. I mean, CTA, SKA, they're not cheap in the absolute sense. I agree. Thanks for the comment.
Okay, so very quickly, I see a raised hand by Sandy Pansangupta.
Yes. Can you hear me, Takeshi?
Yes, please go ahead.
Okay. Yeah. So you said the scaling of the energy density of B square that can be different from 1 by A4. but that should also reflect in the equation of state of this kind of fields, you know, like it won't be a radiation like equation of state. So how does that reflect on it? Is it towards the stiffer side, or so how does the equation of state change from 1/3? That's the question for this kind of behavior.
Sure. So I think I should go back. Yeah. So the point is that the energy density of the gauge field is the sum of the magnetic and electric field.
Yes.
And so this sum goes down like (8⁻⁴). And so in this sense,
So yeah, I see the total composite is still radiation. Yes.
but when
Okay,
you look
but
at individual, when you look at
but
individual,
if you want to mimic this 1/A6 kind of a behavior with some other field, something has to do it, right? Now, does that matter for the equation of state? That's the question. Yes, the total thing doesn't change, that I get.
yeah. So when this is happening, so this is what's happening here is that some part of the electric field is getting converted into the magnetic field. So the sum of the B and E is going down like (8⁻⁴). So, but this is indicating that the electric fields actually go down quicker than (8⁻⁴).
I see. Thanks.
Okay, so maybe it's time to move to the next speaker. So Takeshi, thanks again for this very clear seminar.
Okay, so let me